Look at the gold dial. It stands for one test. A referee tests two separated players. A lucky pair might pass one test, so copy it until the chain fills the screen. To pass the whole challenge, every box must stay gold. One red failure breaks the chain. If the rounds were independent, the chance of cheating through all of them would collapse. But quantum players may link every answer through entanglement. The questions are separate. Their decisions need not be. Could that protect the chain? The answer is no. Any weakness in one test becomes exponentially strong when repeated. Yet proving this was astonishingly hard. We begin with the arrows now appearing. 2 rooms, 1 referee, no secret wire. First, follow who can speak and when. Here's the game. Alice is in the left room. Bob is in the right room. The gold machine between them is the referee. Before play, they may agree on a plan and share entanglement. Then the doors close. No message may cross between the rooms. The referee sends a green question card to Alice and a blue one to Bob. Alice sees only her card, and Bob sees only his. Each returns 1 answer card. The referee compares the questions and answers, then declares a win or a loss. That is the game. The labels below record possible questions, possible answers, how questions are dealt, and which answers win. You do not need to memorize the letters. Follow the arrows. Preparation happens before the doors close. Questions travel outward. Answers return to the center. Nothing passes from Alice to Bob. Now watch one game from beginning to end. That silence is the rule that matters. The 4 windows show a tiny yes or no game. Each player can receive question 0 or question 1. Each must answer 0 or 1. The rule is simple. In the first 3 windows, the referee wants their answers to match. In the last window, where both questions are 1, the referee wants their answers to differ. Can they prepare answers that always work? Start with the upper left window. When both questions are 0, their answers must match. Move to the upper right. Alice's answer for 0 must also match Bob's answer for 1. Now the lower left. Alice's answer for 1 must match Bob's answer for 0. Put those 3 facts together. All 4 prepared answers are forced to be the same. Then the lower right window asks for the opposite. It demands that Alice's answer for 1 differ from Bob's answer for 1. The first 3 windows force them equal. The fourth demands they differ. No list can satisfy all 4. At least one window must fail. A plan can satisfy any 3. So when the 4 question pairs are equally likely, the best ordinary strategy wins 3 games out of 4. Shared randomness only chooses between lists with the same limit. Keep this picture in mind. 3 compatible promises surrounding 1 unavoidable contradiction. Quantum entanglement cannot erase the contradiction, but it can distribute the risk more cleverly. The red mark is not bad luck. It is unavoidable. That is the ordinary classical limit. Now give Alice and Bob 1 entangled pair before the doors close. The 2 wheels show their measuring devices. Each question selects a direction, 2 for Alice and 2 between them for Bob. You do not need the machinery of quantum physics to follow the result. Each answer still looks random by itself, like a fair coin. But when the referee places the records side by side, the answers match and differ in a pattern no prepared list can reproduce. The angles balance the risk across all 4 windows. The formula below says this strategy wins about 85.4% of the time. The best ordinary strategy won 75%. Entanglement adds about 10 wins in every 100 games. If Alice changes direction, Bob's answers alone still look 50-50. The advantage appears only when the referee compares both records. Quantum players are stronger, but not perfect. Roughly 15 games in 100 still fail. What happens when the referee repeats the game and demands a win every time? We may want to multiply 85% by itself again and again. The next picture shows why that tempting argument is not enough. 1 round therefore leaves a real gap below certainty. Repetition should widen that gap, but entanglement makes the rounds depend on one another. The referee now deals many question pairs at once. Alice receives a row of green questions. Bob receives the matching row of blue questions. They pass only if every column wins. If they used a separate strategy in each column, we could multiply the 1 game chance by itself. But the rules do not force separate play. Alice may choose one measurement for her entire row. Bob may do the same. That can link answers in different columns. Imagine 10 lamps controlled by one coin. Heads lights them all. Tails darkens them all. Each lamp is on half the time, yet the chance that all 10 are on is still 1/2, not 1/2 multiplied 10 times. Their individual chances do not determine the joint chance. A repeated quantum strategy is not literally that coin. The example only exposes the faulty step. Independent questions do not guarantee independent wins. The correct calculation is a ladder. The chance that the first column wins times the chance that the second wins given the first, times the chance that the third wins given the first two, and so on. Later factors may change after earlier success. The vertical factors on screen represent that dependence. So the proof must do more than multiply. From a suspiciously successful joint strategy, it must extract a legal one-game strategy. If that beats the one-game limit, we have a contradiction. The challenge is opening the joint strategy without sending information between the rooms or letting rare success distort the measurement. That dependence is the first major obstacle. The next sequence shows the proof's plan before we touch its technical machinery. Here's the proof's plan before any operator appears. Assume a repeated strategy wins every coordinate too often. Choose one coordinate to remain live. Reveal or simulate carefully selected information about the others. Then try to turn what remains into a legal strategy for one ordinary copy of G. The real questions X and Y are inserted into the live coordinate. Everything else must be generated from resources shared before separation, plus information available locally after each question. If the extracted strategy wins with probability greater than omega star, it contradicts the definition of omega star as the best possible one-game value. The decay theorem has become an extraction problem. Locate a favorable region, then make one coordinate behave like an ordinary game. The coral thread marks a promise. Alice's rule never receives Bob's question, and Bob's never receives Alice's. But selecting a favorable region distorts what remains. A successful branch may be extremely rare. Conditioning on it can create correlations and magnify tiny average errors. That is the first obstacle, and 4 cards make it visible. Start with 4 equally likely pairs, 0, 0, 0, 1, 1, 0, and 1, 1. Before selection, the left and right bits are independent. Keep only the event that the bits are equal. The mixed pairs disappear. Among the survivors, 0, 0, and 1, 1 each have probability 1/2. The retained bits are now perfectly correlated, although no message was sent. Selection changed the ensemble. That is conditioning. To make the retained probabilities add to 1, divide by the probability pi of the event we kept. This division is dangerous. Suppose a discrepancy is tiny on average, while the successful branch occurs once in a million trials. After conditioning, the estimate may grow by a factor of 1,000,000. That is the magnification you see. In the proof, the branch probability sits in front of a relative entropy estimate. Dividing it away can destroy exponential control exactly when success is exponentially rare. Dimension-based repairs are unavailable because local dimensions may be arbitrarily large, but finite. We need a numerator that retains the same factor p, so normalization cancels it instead of exploding. Quantum conditional information adds another obstacle. A mixed state can be represented by a vector in a larger private workspace. That representation is a purification. Many vector representatives describe the same mixed information, and locally sensible choices need not agree globally. Think of several calibration frames, each representing a nearby conditional state. Align the second frame with the first, align the third with the second, and continue around a closed loop. When you return, the final frame may be twisted relative to the starting frame. The underlying mixed state has not physically rotated. The picture represents gauge freedom. Different vectors can encode the same mixed information. Pairwise alignment does not guarantee one globally consistent choice. Going around the loop exposes the problem. The leftover mismatch is called holonomy. It is not a signal traveling between Alice and Bob. It is a failure of local comparisons to fit one global factorization. A proof that chooses one preferred square root or phase at every branch can therefore become inconsistent around the network. The breakthrough is to stop choosing one fragile representative. Instead, spread every positive acceptance strength across all positive scales by one canonical rule. This is resolvent purification. Its job is to preserve acceptance weight exactly while controlling how the representative changes. Let F be a positive contraction, a yes or no quantum filter whose acceptance strengths lie between 0 and 1. Imagine diagonalizing it into eigenvalue strengths called sigma. For every positive scale u, the resolvent loom assigns the profile sigma divided by sigma plus u. At small u, much of the component remains. At large u, it fades smoothly. Every eigenvalue follows the same rule. Follow one strand from left to right. Its height records the amount surviving at that scale. In operator form, gamma of f applied to v at scale u is f times the inverse of f plus ui applied to v. Why this curve? Because its total squared weight can be checked exactly. For one positive sigma, integrate from 0 to infinity the square of sigma divided by sigma plus u. The answer is sigma. The moving blade accumulates that area across all scales. Returning from eigenvalues to the full operator gives gamma of f dagger, gamma of f equals f. Notice the right side, it is f, not the identity, so gamma is not being called an isometry. The construction preserves precisely the Born weight of the acceptance filter. The 4 bars on the right recover the 4 strengths that entered on the left. It also supplies a canonical representative, avoiding the inconsistent local choices we just saw. The continuum does not demand an infinite physical strategy. A fixed finite strategy has only finitely many relevant positive eigenvalues. Exact weight preservation is half the breakthrough. The other half is controlling how far these representatives move while a hidden history is revealed. For that, the proof opens an information ledger. Reveal the hidden history in order. In one orientation, Alice's conditional effect updates, while Bob stays fixed. Reverse it to study Bob. Before each reveal, today's filter is the average of tomorrow's possible values. That is the martingale idea. At a branch before it opens, the weighted average of the futures is exactly the present. Now attach an operator entropy, h, 1 of f equals minus f log f. Every movement of the resolvent purification spends gold tape. A one-step movement is bounded by the entropy lost in that reveal. Add the costs over the chain. Each intermediate entropy appears once positively and once negatively, so neighboring terms cancel. The sum telescopes to the initial budget minus the final remainder. Global accounting emerges from local reveals. The size-biased choice of coordinate and orientation makes the live coordinate a uniform martingale increment, while the other player's effect stays fixed. Watch the middle pieces disappear in pairs. Only the ends survive. Each cut represents a proved information cost, not a decorative meter. Most importantly, the accepted branch enters the ledger without discarding its probability p. The unnormalized budget contains p times the branch's surprise, together with answer information already revealed. When the posterior state is normalized, that p cancels the dangerous reciprocal. The proof keeps the factor the naive conditioning argument threw away. The rare branch has not vanished. It is about to pay its information bill. For a branch of probability p, scalar entropy is minus p log p. Conditioning divides by p. Divide the entropy by p, and the result is log 1 over p. That is the crucial turn. A branch occurring once in a million does not cost a million units. It costs roughly the logarithm of a million. Watch the towering reciprocal shrink into logarithmic steps. This is the payoff. If p is exponentially small in the number of coordinates, log 1 over p is only linear in that number. The explosion disappears because the numerator carried the same p that normalization removes. Rare branches are not free. They are priced by information, or surprise, rather than inverse probability. Together with telescoping, this gives a small average distance between the ideal conditional state and versions each player can form locally. But a small average distance is not yet a playable strategy. Alice and Bob must choose nearly the same hidden history and align their quantum states without comparing notes after the questions arrive. The ledger now feeds 2 identical reals prepared in advance. Begin classically. Before the rooms close, Alice and Bob receive identical reels of random candidate histories and thresholds. After their questions arrive, each scans the same proposals using only a local probability distribution. Alice accepts according to hers. Bob accepts according to his. When those distributions are close, their first accepted candidates agree with high probability. The shared reel is old information, fixed before the questions. Nothing travels between the rooms afterward. That is, classical correlated sampling. The quantum version must also align the conditional states attached to the chosen history. The resolvent construction makes those states canonically comparable. A finite pre-shared catalyst helps local unitaries prepare close approximations. Its technical name is an embezzlement state, but the name does not mean information or energy was stolen. Its dimension may depend on the finite strategy and desired accuracy. Again, it exists before the live questions. When histories match and states align, both laboratories hold local approximations to the same ideal branch. Now the choral coordinate becomes real. Insert the actual one-game questions, run the repeated machinery locally, and extract answers under the original rules. Assemble the extracted strategy carefully. Alice receives only the real question X. Bob receives only Y. Each uses the pre-shared reels to generate a nearly matching history. Each locally prepares an approximately aligned conditional state from resources fixed before the questions. They insert X and Y into the same live coordinate of a simulated repeated game. Alice applies the repeated strategy's live coordinate measurement on her side. Bob applies his on his side. They return only those two answers. No post-question message is entered. Check the resource boundary once more. Shared preparation before, local action after, and nothing crossing between. This is a legal finite-dimensional tensor product strategy for one unchanged copy of G. If the repeated strategy had won every coordinate above the permitted rate, the extraction estimates would make this one-game strategy win with probability strictly greater than omega star. That is impossible by definition. Therefore, a universal positive constant CQQS exists such that when epsilon equals 1 minus omega star and is positive, the repeated value is at most the displayed exponential bound for every at least 1. The prefactor is 1. Exponent 13 is not claimed optimal. The question distribution may be arbitrary. Answer sets are finite and non-empty. Local dimensions may be arbitrarily large but finite, and the supremum need not be attained. Every condition belongs to the theorem we have actually proved. What does this theorem change? Its direct application is soundness amplification for finite, two-prover, one-round verification games. If dishonest entangled provers cannot win one instance perfectly, demanding victory in every coordinate of n repetitions drives complete acceptance down exponentially. A constant gap becomes overwhelming confidence. Related tests appear in device-independent cryptography and certified randomness, where untrusted separated devices are judged by correlations. The connection is real, but bounded. Practical key distribution, randomness certification, and verifiable computation need extra arguments, noise thresholds, finite statistics, leakage assumptions, and composable security. This theorem alone does not encrypt a message or secure hardware. It supplies decay. Applications must do the rest. It concerns winning every coordinate, not merely a high average score. The supplied lean artifact formalizes the finite game, repeated question law, all coordinate predicate, entangled values, and exponential interface. Formalization is evidence inside that encoded model. It does not erase the mathematical or application boundaries we have traced. Return to the corridor. 2 rooms, 1 question each, 1 shared state prepared before the doors close. Entanglement can outperform every classical plan, but it cannot carry Alice's question to Bob or Bob's answer to Alice. Now repeat the game independently in times and require victory everywhere. The players may coordinate all answers through one vast joint measurement. The wins need not be independent. That is why the proof needed conditioning, purification, the resolvent loom, the entropy ledger, and correlated sampling. Each device was introduced to repair one precise failure in the naive argument. That is the final lesson. Yet in the finite tensor product model, any real gap below perfect success still grows into exponential decay. The machinery earns that conclusion without assuming the independence it had to prove a round. One failure opens the chain. 2 sealed rooms. No wire. 1 imperfect game. Repeated. And perfection runs out.